Now in today's class we will see how much a language model is good, how good a language model is, and we should also know what are the ways in which we can identify how a language model will perform. Right, so in general sense or in layman language, how would we know that a language model is good or not? So when we say that a language model is, or an n-gram language model is based on probabilities, so it should assign higher probabilities to the real and frequently observed sentences, right? And it should also assign lower probabilities to ungrammatical or rarely observed sentences. So that's the one key principle, that the sentences that are occurring very high, large number of the sentences that are the number of the frequency of the sentences is high, then it should have high probability, right? And that is also in our general common conversation, the probability must be high. But when there is a mistake, there is ungrammatical or there is some other kind of mistake or some sentences that are not very frequently occurring, their probability must be low, right? So in that sense we can say that our language model is good, but we should have some kind of evaluation metric, right? So that needs to be evaluated. For evaluating some kind of model, for any model we have the train test framework. So we generally have a training set on which we build our model, and there is a test set that has never been observed before, that has never been seen before, and that has never been used in the training set, right? So that is unknown to any person, right? So we have some kind of data and we divide it into the train part and the test part, and then we never use this test part, is never used in building model, never used in building model, right? So whenever we say we are training an n-gram model, it means that we are calculating the probabilities, or for the case of bigram we are calculating the bigram probabilities for all the bigrams present in this train corpus, right? So we say that we are training the bigram probability, or we are training the corpus, or we are training the parameters. So these bigram probabilities are actually the parameters of the language model. So that's in the general framework for evaluating a model. Now there are two ways in which we can experimentally or theoretically we can evaluate the n-gram models. So once we have a language model, right, so we can put it into a task. A task is actually a problem, like spelling corrector, speech recognizer, machine translation system, and named entity recognition, sentiment analysis, right? So these are the different tasks in which we can put into a language model, and these all NLP tasks do require and necessarily they require a language model for their execution, right? So whenever we are solving some task, we are having some task, and we need to build some kind of model for that. So we have to necessarily we do require some kind of language model, right? So it may be an n-gram language model, but it may be some other kind of model. But each NLP task, it is a preliminary requirement that it should have a model, language model. So very starting language model was the bag of words model. So bag of words is now in respect of n-grams, it is corresponding to unigram model. We just have the count of all single words, and bag of word model says that given a document is composed of words, and then we represent this document with the help of a document term matrix, document term matrix, right? So in which we, on the rows we have the documents, on the column side we have terms or words, and then for each document, for document 1 we put the count of these. So if the document 1 is having 3 words of W0, so or T0, T1 and so on, we have V vocabulary, number of vocabulary all present in the column. So this is document 1 is having 3, 6, 0, 8 like this. So 3 terms of T0, 6 terms of T1, 0 terms of T2 and 8 terms of T3 and so on. So in this way the bag of words is represented with the help of a document term matrix, right? And then this document term matrix can be applied into some kind of task like sentiment analysis, right? Or spam detection. So we can identify that this particular document is what is the sentiment of this document, right? So document may be a single sentence, it may be a tweet, it may be a large paragraph. And similarly in spam detection we may identify whether this particular document is a spam or not, right? So in this way we can apply a language model in a task and then we can accomplish that task, right? So without generating this table we cannot put any kind of document or language or any kind of sentences into this task, right? So in case of bigram or trigram or n-gram, we have, instead of terms we are having the bigrams here at this place. At the columns we have the bigrams, trigrams, etc. So we can also have n-grams, right? So in this way we can generate the language model and put it into a task and then execute the task, and then we can finally check out with the help of the accuracy for both the language models. So if we have two language models A and B, right, so we do the same sentiment analysis for the bag of words, and we do it for bigram, and then we calculate the accuracy for both, or we calculate the F score of precision recall for both. Similarly we do for sentiment analysis and spam detection for both, and then we check out with the accuracy. So but in all these things it is actually a very time consuming task and resource consuming task, right? So there must be some very preliminary evaluation method in which we can judge, or we can, by applying some formula or by just a simple calculations, we come to know some rough estimate of the language model, or the rough estimate of quality of language model, right? So for that we have the intrinsic evaluation. Extrinsic evaluation means we are just taking the language model as some piece of thing and putting it into a machine, and then machine is giving me that out, right? So this is a language model, this is a machine, and we are giving a language model as an input, and this is giving me some parameter or some metric like accuracy as an output, and then I am comparing. So I am giving language model 1 to this machine. After some time I am giving the language model 2, right, to the same machine, and it is producing some accuracy. So this is like very cumbersome task, and this is an extrinsic kind of evaluation, right? So the extrinsic evaluation is again, you see here, time consuming, and so we require an intrinsic evaluation in which we can, within the language model, we can see how a well language model is built up, or how good is a language model, or how not exactly a very good estimate, but it may be a bad approximation. It may be a bad approximation, but it will give some kind of initial and starting idea of the corpus, that this corpus, or on this corpus this particular language model may perform better, right? So that for that we have the perplexity, right? So perplexity is actually again based on the probabilities, and the intuition of perplexity is again from the Shannon proposed some idea that we can evaluate a language model by applying a simple task, that how well we can predict the next word. So this the simple task, and this is very, you can say, the common and very simple easy task in which we can apply some kind of language model and test its performance, right? So we have some accuracies, we have some probabilities here, right, from a language model. So these probabilities will let us know if we are trying to predict the next word or an upcoming word in a sequence of words or sentence. So I always order pizza and cheese with mushrooms and pepperoni and anchovies, fried rice. So we have different probabilities, and we will pick up some kind of highest probability here. So we can put up mushrooms here, right? So the probability of mushrooms given and this sentence, and pepperoni given this sentence, and these anchovies given this sentence will be calculated, and then we can have the highest probability among these. We can choose that one, right? So similarly we can have different, we can test it on different sentences, right? So this is the idea that was given by Shannon, so to predict the next word, right? So the perplexity is also something like that, not exactly like that, but the perplexity formula is this. We have some kind of sentence in which we have n words. So the probability of this sentence, right, having n words to the power of 1 by n, right? And this probability could be, this thing could be any kind of probability. It could be a bigram probability, it could be unigram probability. So depending upon the language model, right? So we can calculate the probabilities generated by a different language model, right? So a language model based on the chain rule, we will get this formula. A language generated by bigrams, language model generated by bigrams will be this formula, right? And for unigrams, the perplexity of the sentence is equal to under root n product of I is equal to 1 to n 1 by simple p of wi, right? So this is the unigram probability, and we have put this in the formula. So we get one perplexity by this, we get one perplexity by this, we get one perplexity by this, and then we can compare all these, and we can see if the perplexity is lower, then better is the language model, right? So if, for an example, if we have some kind of random digits and we need to recognize those digits, right? So each digit has a probability of 1 by 10, right? So if we are in general saying that each digit is equally probable, right? So the probability that will be assigned to each digit will be 1 by 10, right? This is just an assumption here, right? It may not be necessarily that we have to take 1 by 10, but if we have we don't have this assumption, we take in actual case the probability will be different for each digit, right? And those probabilities will sum up to 1. So but for this assumption, we are assuming that each digit is having the equal probability. We can assume it as 1 by 10. So 1 by 10 to the power n. So we have 10 digits, right? And we have, if we have a 10 digit number, right? So we have all these 10 digits. Each W0, W1, W2 we will have 10 of these words, and each is having 1 by 10. So 1 by 10 to the power n to the power minus 1 by n will lead to the perplexity of 10, right? But this 1 by 10 to the power of n is, in that case, when we are assuming that p is 1 by 10 for each of these digits. So this could be something different one, right? So if we are having some, say suppose some different probability, it could be like 1 by 9 dot 1 by say 20 dot 1 by 50, right? So this can also be done in the same way, to the power minus 1 by n, and that will lead to some different value, right? So also on Word Street Journal, taking the corpus as Word Street Journal of 38 million training words, the perplexity is calculated for 1.5 million test words. The perplexity obtained for unigram model is this 962, for bigram model is 170, and for trigram model is 109. So we see here for the trigram model the perplexity is lowest. So we can conclude that this for a preliminary, before applying it to a task, we can just directly take here the trigram model, and then we can take a presumption that this trigram model will work better in some given task, right? So this is now again some more detail about the Shannon's visualization method. How do we again generate the sentences? This is the experiment that is carried out mostly when people generate or people propose some new language model, right? Or people propose some kind of new technique to represent the sentences, or people generate some kind of some new kind of technique for a classification method, or that can be applied into NLP. So this is a very first hand method people apply, and then people check out or visualize. This is actually the visualization method. Visualization means that we can read it, and then we can identify that what kind of output we are getting, right? So for a given corpus, we are able to calculate all these bigram probabilities in the form of these tables, right? Bigram table or bigram matrix. We have a bigram matrix. So for a given corpus, this is the 0, 1, 2 and up to V. This is also up to V, right? We can generate a bigram matrix for a given corpus. Okay, we can generate bigram matrix for a given corpus. In more technical terms, we can say that this is also equivalent to we train bigram probabilities on a given corpus, right? So in more technical sense, we can say that we have trained the bigram probabilities on this corpus, and we have obtained this matrix of bigram probabilities, right? So this is actually these are actually called as the parameters of that model, right? Now how to visualize? So I may choose some kind of a random bigram, right? So suppose I choose this start and some word. So if I choose start I, right, then from this table I will see what is the probability, or which word is having the probability, highest probability, followed by I, right? So if somewhere this I is present here, right, and somewhere want is present here, and there are some other words present, so this want is having the highest probability, this is having the highest probability, we see from this corpus also. So yes, from this, so this is the same table that we need to generate, right? And then if we take some, the random sentence, so if I take start and some random bigram and start I choose this one as a random bigram, okay, then I will go to I, and then I will see this is wi minus 1 and this is wi. So I will check out from these whole number of words which word is having the highest probability. I see that this I eat is actually having here the highest probability, right? So in that one, in this one, so for this corpus I eat is not the highest, but I want is the highest, right? So I will go to I and then see which is the having highest probability. This is, so want is having the highest probability. Again, then I will go to the next word is want now. So I will find out in the row of want which word is having the highest probability. Maybe want 2 is having the highest probability, so this 2 is having the highest probability somewhere here, right? So similarly I will look into the next word that is having highest probability. So in this way I can build up a sentence, right? By initially choosing a random bigram, I can build a complete sentence until I get the end of sentence, right? And then I can put up all these together, and then I will get the complete sentence that will be generated by the machine, right? So based on the language model and giving it an initial random bigram, the machine can generate this kind of sentences, this kind of sentence. So these people have done a lot of experiments, right, on different corpus. So on Shakespeare, when people did this, people did this experiment of Shannon visualization. So and then they generated the sentences by the machine. So giving the 2 as the starting word, right? Giving 2 as a starting word, they have obtained, in case of unigram, to him, swallowed, confess, here, both. We can visualize that whether the sentence is correct or not in grammar and in most of the language part, whether this sentence can be said correct or not, right? So in case of bigram, what means sir, I confess, she. So this is somewhat better than the unigram model. Then we see the trigram model, sweet prince, Falstaff shall die. So this is from Shakespeare. So those who have read the poetry, they may more recognize these kind of sentences. But in case of quadrigram, we see King Henry what, I will go seek the traitor. So this is as we are moving on towards the higher n-grams, we see that the language is a little bit improving, right? So this is in the Shakespeare corpus. We will see this in the case of Wall Street Journal. We see now unigram months, the Maish and issue of year, right? Last December, though, the way to preserve. And in case of trigram, they also point to 99.6 billion from 200. We see that in this trigram, the visualization is quite better, right? So this visualization method can also be applied to lot more types of corpus. we have applied here to the Shakespeare corpus, to the Wall Street Journal. Now, what could be the different corpus that can be applied? So it can be applied to scientific research papers, right? I can just train on the Google Scholar database, and then I can try to write some kind of scientific language, right? So in that case, it will generate the scientific language. People have also tried, very unique example is that they have taken the set of question papers that we give to the students for solving in exams. So people have taken the set of question papers, and then they have trained these language models on those question papers, and they have tried to generate the question papers from those language, with the help of those language models, and they have seen like they do not make much sense, but they are pretty good in the language that is being generated. Similarly, people have generated the music also. So in case of music, these the the sequence of music, these small these components are represented with the help of letters, right? Small and capital letters. So they have again trained the music, and then they have tried to generate the music also. So people have done different kinds of experiments with this Shannon principle, and in some of those they have visualized that the results are quite good, right? So the problem with this bigram, or in general n-grams, is that there are a lot of zero entries in the tables, right? So in case of Shakespeare corpus, so there will be, for 29,066 unique words, there will be 844 million possible bigrams. So this is the size of, or length of, the bigram matrix. So 844 million is one side, either row or column length. So if we see the 84647 in the 844 million, it is only, the zeros will be around the 99% of all that matrix, right? And as we move on to the higher n grams, this is only for bigrams. As we move on to the higher number of n grams, the number of zeros is more increasing, right? So this bigram matrix or n-gram matrix has to be represented in some kind of sparse matrix representation in practical sense, so that it does not occupy, or it does not waste the space. So that's the problem, some kind of space problem, or we have to deal with the high number of zeros that are present with the bigram or n-gram matrix. And so these n-grams have some problem that is called as overfitting, and we need to have some kind of technique through which we can overcome the overfitting of the language models, or so that these models are able to generalize better on the test set. So we will be seeing what kind of overfitting is there, and how to solve that kind of overfitting problem.